In this section of chapter 21, we will discuss about belt of stability, magic number, modes of radioactive decay, and balancing. Now, nuclear instability could be due to a number of reasons. If a nucleus has too many protons, it would be unstable. Too many neutrons, it would be unstable. If it has a big mass, large mass, it would be unstable too. Now, what is belt of stability? Scientists took into account all the stable nuclei and plotted their number of protons along x-axis and number of neutrons along y-axis. And all these stable isotopes show that these points fall on this line, a curved line. Beyond 20, it goes upward. And that's called belt of stability. See, all those nuclei or isotopes falling within the belt of stability are stable because that's how they are plotted. Having number of protons falling in here means too many protons compared to neutrons. So bottom of the belt of stability would represent too many protons. The top of belt of stability would represent too many neutrons. So change would happen accordingly. Let's try to understand more about belt of stability. If there is an atomic number less than 20, number of proton for the most stable isotope would be equal to that of number of neutron. For example, think about lithium. Lithium has 3 protons and 3 neutrons, that makes it 6. And that's within the belt of stability between 0 and 20, between 1 and 20, and that's, since it falls on the belt of stability, it is stable. Similarly, you can say oxygen, atomic number 8, number of proton equals to number of neutrons, so that it must have 8 neutrons, so that makes 8 plus 8, 16. That's also stable and falls on belt of stability. So it's pretty easy to predict those stable isotopes which falls within the belt of stability having atomic number 20 or less than 20. When it is more than 20, number of proton is no longer equals to number of neutrons. Number of neutron exceeds number of protons. Why? When atomic number is more than 20, let me show you pictorially, there are quite a few protons in the nucleus. So since protons repel each other, it needs more neutrons to sit in between. So let's use a different pen. So we need neutrons in between. So we need more neutrons now. Just same number of proton as neutron does not make it stable. So you need more neutrons which are neutral charged. You can think in terms of lowering this repulsive forces because neutrons would take their place in between protons. Now, if you look at belt of stability, it doesn't exceed beyond 83. What that tells us that atomic number greater than 83 would be unstable. So there is no stable nucleus having atomic number more than 83. So toward the end of periodic table, each element that you see is unstable and would give off different types of radiation. Here we are showing you how uranium breaks down. So you start with uranium here, 238. It goes through a series of processes in which alpha, beta, alpha, 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 all these different particles come out. And eventually it changes into lead, Pb, having atomic number 82. In addition to belt of stability, we can also explain nuclear instability based on some other observations. One of them is called magic number. Scientists noticed that a nucleus with 2, 8, 20, 28, 50, 82, and 126 number of protons or neutrons are more stable than the other numbers. And so these are called magic numbers. So nuclei with magic numbers of protons and neutrons are more stable than their neighboring ones. As an example, helium having 2 protons and 2 neutrons, and both are magic numbers because 2 is a magic number. On the other hand, helium-3, this is an isotope of helium, having 2 protons. Keep in mind, helium will have to have 2 protons because atomic number 2, as long as you talk about helium, we're talking about atomic number 2. If atomic number changes, identity of the element changes. Okay, so helium-3 would have 2 protons and 1 neutron because top number is mass number, which is given by number of proton plus neutron. Now here we have one magic number because 2 represents a magic number but 1 isn't. And between these two, helium-4 and helium-3, helium-4 is more stable. We can also explain nuclear instability based on odd-even rule. Again, this is purely an observation. Scientists noticed that out of all stable isotopes, 157 stable isotopes have even number of proton and even number of neutron. On the other hand, there are 53 stable isotopes which has one even, the other one is odd, even proton, odd neutron, and 50 stable isotopes with odd proton and even neutron, and only 5 stable isotopes with odd number of proton and odd number of neutron. So based on this kind of observation, scientists think that even number of proton and even number of neutron must provide additional stability to these nuclei so that they are stable. Here we are going to discuss about mode of nuclear disintegration or decay. That can we predict how a nucleus is going to break down based on the following criterion. If a nucleus has too many protons, keep in mind too many protons relative to belt of stability. That means if it lies below the belt of stability, number of protons lies below the belt of stability, then what kind of decay or disintegration is going to happen? Carbon-11 is a good example of that, having 6 protons and 5 neutrons because top number is due to proton plus neutron. Now this has too many protons. So obviously nature is trying to reduce the number of proton. So whenever I'm asking this question, will number of proton increase, decrease, or remain the same? Since instability is due to number of protons, so obviously the natural trend would be to decrease the number of proton. So that's why we have here proton must decrease, number of proton must decrease with time. Then we need to think about what kind of particle would come out so that number of proton decreases without any big change in mass. We know that in nucleus there are 2 particles having almost same mass, which are proton and neutron. So when proton needs to be changed, you can always assume that it's changed to a neutron. So write down neutron and then balance it with a particle X. Then we identify particle X. When you balance it, you know that neutron has 0 charge and unit mass. So the new element, unknown element X, unknown particle X, would have bottom number 1, top number 0, because that way you would have 0 plus 1, that would be 1 on the left side, and 1 plus 0, I'm adding the top numbers, that balances top number on proton. So let's identify now X. 1 positive charge, but no mass, and that's positron. When you say no mass, it's pretty small mass, so we just, for practical purposes, we ignore that mass, which would be mass of an electron. To be more accurate, it's 1 over 1837 mass of a proton or a neutron. Now, carbon 11 has too many protons, so positron would come out and it changes into X. Now we identify X by looking at the bottom number. By balancing, we find out the bottom number, which is 5, and look at periodic table. Atomic number 5 is boron. So X represents boron. In other words, carbon 11 after positron emission is changed to boron. Nuclear instability can also be due to too many neutrons relative to belt of stability. So these are cases when number of neutron is lying above the belt of stability. So you have too many neutrons, natural trend is need to decrease the number of neutron. So here I raise the same question, like will number of neutron increase, decrease, or remain the same? Answer is going to decrease because instability is due to too many neutrons. Again, we'll be looking for particles that would keep the mass about the same. And we know that protons and neutrons have about the same mass. So when you are trying to decrease neutron, our first assumption would be let's consider having a proton converted to a proton, and it's indeed the case. So you put down proton and X. Proton has 1 and 1, and then find out what X is by balancing. Remember, the top number, bottom number will be added to 0 because on the left hand side we have neutrons. So I must have minus 1 underneath X, and I must have 0 on the top. Then 1 plus 0 is 1, which matches the top number. And minus 1, I think my minus 1 is not very distinct here. Let's rewrite that so that you don't get confused. Let's rewrite this. X minus 1 and 0 on the top. That way, minus 1 plus 1 that you have on the proton, that gives 0. So let's identify this particle. Minus 1 means it has a negative 1 charge, but mass is almost 0. And so it has to be an electron, or emission would be beta emission. So beta emission changes neutron to a proton. Now, third reason why a nucleus could be unstable is due to its mass. Too large of a nuclear mass would have too many protons, and that's why they're unstable. I have already mentioned that when atomic number exceeds 83, none of the nucleus is stable because they already have too big of a mass. Again, the natural trend is if you have too big of a mass, the mass has to be decreased as quickly as possible. So among the possible decay mode, we need to think about what particles can come out: alpha, beta, gamma, positron. Out of these particles, which one would be most massive? As you can see, alpha will be most massive, having 4 mass number. So we can say when atomic number exceeds 83, all of those nuclei are massive, and they would reduce its mass by predominantly giving off alpha particles. So mode of decay is going to be alpha emission. So uranium-238 is one of them, having 92 protons. That is greater than 83 proton for belt of stability, and that's why alpha would be the major mode of decay. Now, by saying this, I'm not saying that beta or gamma doesn't come out. As I've shown you 2 or 3 slides back, that uranium goes through series of stages before it changes to lead. And out of all those stages, alpha emission is the most important one and dominant one because that decreases its mass rather rapidly. Now let's go over this problem. Question is, which of the following are radioactive based on belt of stability? Oxygen, 8 protons, so let's write down here, plus 6 neutrons. 8 protons and 6 neutrons. Now 8 protons is below 20, so number of protons should be equal to number of neutrons to be most stable. So obviously oxygen 14 cannot be stable. Then sulfur 16, 32. So 16 protons and 16 neutrons. Same number of proton as neutron. So it falls on the belt of stability because it's below 20. So it's quite stable. I don't need to worry about that. Polonium 84. This goes beyond 83. So these are all unstable. Too large of a mass. So in this case, there are 2 isotopes which are unstable, which is oxygen 14 and polonium 208. Now this is problem number 60, and I have picked one of them. This is the reaction given: uranium 235 reacting with neutron, giving Sm 160, Zn, zinc 72, and you need to find out how many neutrons would balance it. How do I do that? Of course, your bottom number and top number has to match. Let's first check the bottom numbers. 92. So 62 plus 30. So that checks out. 92. I don't need to do any kind of balancing. Top number, the masses. 235 plus 1. So it'd be 236 is the total mass. Right now we have 160 plus 72. So that gives you 232. So it's 232 at this point. You have one neutron brings 1 unit of mass, and I need plus 4. So that means I must have 4 such neutrons coming out of this reaction. So this is going to balance the reaction that we are looking at, and all the other balancing can be done in similar manner.